Okay, so yesterday we talked about the ideas of how many shells or orbits are in a diagram, how repulsive or what kind of obstacles are being created by these shells. We also talked about nuclear charge and the number of protons. And when you have increasing nuclear charge, then you're able to pull electrons in closer, creating a smaller atom. We talked about atomic radius. So atomic radius was the distance from the nucleus. Again, we're going to eventually not think as flat Bohr did, but that's okay, flat orbits. The outer boundary of the electrons. So again, I said yesterday, you do not need to reproduce this picture. I just tried to introduce you to really what an atom looks like, sort of fuzzy cloud-like region, as opposed to the rigid flat orbits like Bohr said. Okay, so as you go down a family, then we start with atomic radius because, of course, as you go from period or row 1 to period or row 2, etc., then you have more shells or orbits or energy levels, which you would have talked about that pattern at least in grade 10, maybe even in grade 9. Okay, so don't push out of your brain things you already know. So period 1 has 1, period 2 has 2, period 3 has 3. So we have an increasing, that's bad English there, number of energy levels, and we also have an increasing shielding effect. So I just included this picture, which looks potentially similar to ones that you drew. This has 1 shell, this has 2. Very, very simple, okay? Now, I put stars beside increasing the number of energy levels and increasing the shielding effect because these 2 items, or 2 criteria, have such an enormous impact on all of the trends. So, but just to be extra clear and extra good in our explanations, you're going to see this one as well, okay? And this says, although increasing nuclear charge, like you're going to get more protons, right? The atomic number is obviously increasing. It's actually more of an impact to have more shells and more shielding than the nuclear charge. So when you get to the unit test and you might have to explain, then including this, you don't need to worry about. Basically, you're just going to worry about these. How many shells are there? If there are more shells, there's more repulsion. Okay? More shielding. We did write the definition of what a shield was yesterday. My little Spartan soldier was the little picture on there, but just to remind yourselves. So up and down is obvious in something, but across could be left to right or right to left. So that's tricky. So what we're going to do when we talk about across, we're always going to do left to right because we're English readers, and that's going to that also follows atomic number. So on the left in a period would be a lower atomic number, on the right would be higher, okay? Which means that you're going to increase the nuclear charge. For size, then, if you have the same number of orbits in one period, then you can't think of that anymore as making the atom bigger or larger or smaller. So what's going to happen? So that second picture, the horizontal one, where when you have one proton, one electron, one hand being held, they can get away from you. When you hold two hands of somebody, you pull them in closer. So the more protons, or the increasing nuclear charge, because now increasing energy level diagrams isn't a thing when you just go across, right? So the only factor that's changing and influencing the size is the nuclear charge is increasing, so the atoms get smaller. And the number of orbits, of course, is the same. If you would like, a different way of thinking about that, hopefully that's not like that in your note. There is more protons attracting the electrons, pulling the electrons in their orbits closer. So from your assignment, you should have had in the atomic radius graph. So element 1 is 32 picometers. Element 2, is 31. Okay, that's less. That's not very dramatic. Let's go to period 2. So 123, then all the way down to 90, then all the way down to 82, 77, 75, 73, 72, 71. So your peak would have been an alkali metal with one valence electron, and then your noble gas should have been the valley with 71. So quite a bit of a difference. So that's why one of the strategies we use to help you remember this is to do the graphs, because you can see the dip. Okay, so the next page has my next page, not your next page, has the question. So you're going to find in your little package of elements sodium, which is Na, and argon, which is Ar. Please. And again, if you would like more, I do have more. If it feels like it's too far away. Do you want more? Okay, so show me what you've got. Which element has a larger atomic radius? You could even think of it as is larger. You can show me sodium or argon, or you can show me a question mark. But I want to see it. So hold it up. I have terrible eyes. Show me what you've got. Sodium or argon? Yes, good. Now, try to, when it gets trickier, try to fight your instincts and don't say it out loud. Just show me your little symbol, but that's okay. So, what I want you to do, we're going to draw some summary arrows, okay? So, you have to turn the back and then one more at the top here. I tried to make a little legend for you already. You can just, I'd left a little box there. If you are going to use different colors, pick a color, okay? So I'll do blue. Blue basket, if you want one. So some students will, when we do these summary arrows, after we do all 4 of them, then what you'll see is there is a pattern. However, some students, once we draw all 4 of them, they're like, Ms. Todd, I never want to look at this again. That's okay. So if this is helpful for you to study these trends, great. If you don't like it, I'm never going to ask you to reproduce the arrows. Okay? So let me just say that. So we are going to draw a summary to show the trend in atomic radius. And I'm going to draw all 4 of them as increasing. So when you have atomic radius, you just told me that sodium is larger than argon, which means that it increases this way, okay? I have to go backwards. I apologize. Whoops. No, I don't. Yay. Okay, so atomic radius increases that way and down. I showed you a short form. You can call it AR. You can write the words out. It's also numbered. You could even put the number 1 if you like. We're going to do 6. 1, 2, 3, 4, 5, 6. They're all numbered. So you decide how you want your arrows to look. Okay? Okay, so now we're going to go to number 2. So you have to flip your page back, basically, when you've got the arrows however you want them to look. Okay? So on to ionization energy. So yesterday we wrote this down so that you were able to do your assignment or start the assignment. Energy necessary to remove an electron from an atom. So this trend is usually easy to understand for students. It's okay because if you say the words energy required, energy necessary, then generally speaking, we think of that as being work, right? That requires energy. That's harder to do. Okay? So if it takes a lot of energy to remove an electron, then it's not easy to remove electrons. So for this trend, one of the things you can do is think about a piece of information that you already know. So it says if metals tend to lose electrons, we already know that they tend to lose electrons. Should it take a lot of energy to do that compared to nonmetals? No, that doesn't make sense. Why would they tend to lose electrons then? Atoms do not want to waste energy. Okay, so metals tend to lose. They have a low amount of energy required. If nonmetals tend to gain, they have a higher amount of energy required. Okay, so without even drawing the arrows or thinking about what the trend is and writing the criteria as they're shielding, whatever, let's predict. So if we have chlorine or sodium, which one would have a higher ionization energy? Which one would require more energy to remove electrons? Chlorine, which is Cl, or sodium, which of course is Na. I need to wear my glasses. Or you can put up question mark. That's fine too. Okay. Wonderful. It is chlorine. Now, what we are going to do, again, we'll discuss the trend specifically in more detail. But when you do these, when you have some of the trends, not unlike atomic radius, then ionization energy makes sense with what you already know. And please remember too, let's say you're like, oh, I don't remember what sodium is. Sodium is an alkali metal. It tells you, okay? So your periodic table is your new best friend. Okay, so we predicted chlorine because it is a non-metal. We don't even think of it as losing electrons. So of course it's going to take too much energy. So one of the things that you're going to do in the later questions of the assignment, 4 and 5, and then you're going to make your own predictions in 6 and 7 and 8. So if you started that question, that's great. If you didn't, that's okay. That's what you can work on after the note because they are related. So when you go down a group, the ionization energy is going to get smaller. It's going to be easier to remove electrons. And why is that going to happen? What happens to the size? It gets bigger. So then all that stuff we talked about yesterday, the electrons do not feel the positive pull of the nucleus. They are easier to remove. So as much as we are going to talk about each of the trends separately, you can sort of connect them as well. Okay? So it decreases as you go down a family. So you're going to see similarities with atomic radius because you have more shells, radius increases, which makes more repulsion. And again, that's sneaky number 3, but we like the first 2 better. For going across, I can see that I left a little hint there. But as you go from left to right, so we'll try to always do the same sort of thinking. When you go from left to right, now your atoms are smaller, okay? But also you can do the prediction like we just did. Sodium and chlorine, and they are on opposite sides of the periodic table. So metals or non-metals are on the right-hand side. So the farther to the right, you wouldn't even think of elements as losing electrons. So that sort of thinking can help you check your answer as well. So it increases as you go across. We've just never talked about why. Why do they tend to gain instead of lose? They have a smaller atom, which makes the opposites attract. The nucleus is more attractive to electrons, and if you're attracted to something, you do not let it go. So in the end, when we get to the unit test and you have to explain, you could explain this saying the nuclear charge increases. You could say the number of protons increases. That's the same. You could say the distance of the outer electrons to the nucleus is decreasing. You could also say the atomic size is decreasing. Those are also the same. Okay, so there is a bunch of ways to say the same thing. All right, so the prediction question is right there for you. So now find I and F. So FR is francium. Not that, I mean, you could use that one, but I or F, which one is going to have a smaller ionization energy? Fluorine, F. Okay, so I just tricked you, didn't I? It was increase, and now I've said smaller. So make sure I encourage you to read the question carefully as well. Not that I'm trying to be a trickster, but sort of. Okay, so which one now is smaller? We're not doing increasing anymore. Which one's smaller? Yep. Okay, so this is a nasty question as well because neither of them you would think of as losing electrons. So then you kind of have to remember the trends. So this for sure is the most difficult topic we've done by far. Okay, so we're going to do this. During the note, we're going to try to do predictions. Then there's a worksheet to get you to predict and explain. There are questions in the textbook. And then tomorrow we're going to do review activities together so hopefully one of those things will speak to you and that will help you to remember this. Okay? So that's what I'm hoping. Okay, so go back to your summary. And again, so ionization energy is labeled number 2. You can put the short form. You can pick a different color and fill in your legend. You do what you want. So I know that I'm tricky because I have a new one, but I can even go back to my old one. So what you can do, and again, so sometimes students are like, once we're done them all, students are like, oh, Ms. Todd, I am never going to look at this again. Okay, take it easy. But so you kind of have to decide, in the end, is this helpful for me or not? Okay, so we just said that it decreases going down, but because we want to draw arrows that will help us summarize, I'm going to draw an increasing arrow. Okay. Oops, that is not an increasing arrow. So this is what you have should have seen in your assignment. Wherever the peaks were in the one graph should have been the valleys in the other graph. Yes. Yeah, it decreases going down, but because I want to draw all the arrows increasing, so I'm going to draw it the other way. Okay? Because one of the things that you can do, again, to try to, once you've written an answer, kind of check it, is related to atomic radius or size. So what you're going to see is all of them look similar, except atomic radius. It's opposite.
Thank you. I'll bring it back.
Okay? Oh, no. So then turn your page back over and we're going to do electron affinity, which is not which is not a definition that you have written down yet. Yes. Mm-hmm. We okay? Okay, so write down the blue definition, please. This can be an annoying trend because it is almost identical to ionization energy. The key difference is it says energy released, not required, and this time electrons are being added, not removed. Okay? So when energy is released in science. That's why we, maybe you thought to yourself, why do we keep burning fossil fuels if they're so bad for the environment? Why? Because there's such an incredible source of energy, okay? So when energy is released by a process, that is a good thing. So metals which lose electrons, they will not have a very high amount of electron affinity. And if nonmetals gain electrons, they will release a larger amount. The word affinity sort of implies, like I like electrons, which works here, except the definition has to do with energy. So yes, it works a little bit, but not totally. Okay, so you're welcome. This is often the most difficult definition to remember for students, okay? But it does follow what you would have expected, sort of. So which element is going to have a larger electron affinity? So find sodium, Na, or chlorine, which is Cl. So again, metals are going to lose electrons and release a small amount of energy. Nonmetals gain electrons, so they release a larger amount. So if I give you a nice question like this, which is metal versus nonmetal, then it's a little bit easier to do. When I sneak in the group one, that's when it gets tricky. Amazing. Oh. Don't let them see it. Try to get along, friends. Great job. Chlorine. Why chlorine? It's a nonmetal. So eventually, obviously, we're going to go through up and down and across like we've been doing. But again, most of you got chlorine because you knew that nonmetals lose electrons. Okay, so don't push out of your brain things that you already know. Please don't wreck. I want these back. Don't wreck them. Okay, so as you go down a family, it's going to decrease. So it's not going to release a lot of energy when you add an electron to a big atom. A big atom, the nucleus is not very attractive. So it doesn't want to, electrons don't want to come there. So atomic size increases. You could write the number of shells increases. All of those things are the same thing. And then, of course, number 2, shielding effect increases. And we have to put that third one, but we really don't need it. Okay, so a larger atom with many energy levels is not going to be attractive to an electron. Its nucleus, that's positive, is too far away. So when we go towards fluorine, then it's going to be smaller. You're going to pull it in closer. So now the nucleus is more attractive. So again, you can write nuclear charge increases. You can write the number of protons increases, making the atom smaller. So then the nucleus and the atom itself is more attractive. Yes. And say, or even atomic number, you could write that. That's all the same. Yep, for sure. So the next two, this one, electron affinity and electronegativity. The only problem with this is the noble gases, because according to the trend, then that means that the nuclei of a noble gas should be the most attractive. And you know that we say noble gases don't naturally react, so their nuclei are not attractive at all. So sometimes what you'll find is people will, so when we draw our arrows, you can stop at the halogens and not include noble gases. And we're gonna extensively use a table on the back, which is electronegativity, and it actually just gets rid of it. It doesn't even have a column for noble gases. Okay, so for that reason, because this sort of has to do with reacting. So as the nuclear charge increases, the volume or the size of the atom decreases. The atom will be able to pull electrons in. They are more attractive. So more energy is given off when a smaller atom with larger nuclear charge receives an electron. Okay, so you guys have, I tried to pick an element that we don't often use. So I picked tellurium, which is Te, and oxygen. So they're in the same group. So I picked larger again. I should have picked smaller, but that's okay. Which one has a larger electron affinity? Oh, let's all be on team chemistry. Oxygen is here, tellurium is here. 52. All right, great job. Okay, so oxygen. Okay, so pick another color, go to your summary. I'm going to pick green, but you do not need to. Okay, so in the same way, we're going to draw increasing arrows. So it's up to you. Technically, noble gases are not applicable here. So if you want, that's not right. Stop your arrow there, if you want. You could draw them at the bottom too. Doesn't really matter. You could draw them on the right-hand side, the left-hand side. That doesn't matter. I'm just too short to do any more on my same one, so. We only have one more, so we're almost done. If you include the noble gases, I wouldn't mark you wrong, and I promise I will not give you that as a trick, okay? For the next two, electron affinity and electronegativity. Yes. Mm-hmm. Okay. So electronegativity is a term we are going to even use after chapter 1. So this is a very, very, very useful trend. Because of course, chemical bonds, that's what we're about, right? So giving a qualifier for a chemical bond is going to be useful for us. So last year you should have talked about ionic compounds and molecular compounds. And this year we're going to actually take it a step further and look at, in a molecular compound, there's actually two different types. So one of the ways you can tell the difference between the two types, because they're all nonmetals, then is the tendency of the atom, when it gets in a bond, to pull electrons towards itself. So we'll revisit the definition, transferring, sharing electrons. So sometimes people will short form this to be electron greedy. If an atom is electron greedy, then it's going to steal the electrons towards its nucleus more often. So, there's a cheesy analogy. If I had a cookie, smile cookie, and I broke it in half and gave it to my two small children, would my older daughter give her little brother the bigger half? No way, right? So sharing can be sketchy. Transferring ionic is boring, plus minus, plus minus. So what you'll see is when you have electronegative elements, then strange things start to happen. So we'll scratch the surface in grade 11. And today in my grade 12 class, we actually did advanced Lewis with elements that have really high electronegativity. So these values are so useful, we've actually given them a reference value. Okay? So electronegativity is, the trend is the same as electron affinity. The definition is just a little bit different, but the same ideas. Atoms with high electron affinity have high electronegativity. The trend in electronegativity is exactly the same. Sorry, I started to use the short form, but I didn't put it there like the other ones. I apologize. Okay, so all related to the same thing. And if a nonmetal is small because of its nuclear charge and the number of protons, it is attractive to electrons. So when you have attraction, it holds them in close, giving off more energy when electrons are added, which is electron affinity. It's more greedy for electrons, which is electronegativity. And then the last thing we're going to talk about, so number 6, it's also more reactive. Okay, so they're all kind of related. Yes. So this time I gave us a metal and a nonmetal, but also in the same group, nonmetals. So let's do sodium and chlorine first. Which one is going to be greedier for electrons? And again, you can think of the trend or you can think of what you already know. You could even think of this like which one tends to gain electrons. Sodium, a metal, or chlorine, a nonmetal. Wonderful. Chlorine. And then trickier a little bit in a group, iodine or iodine and fluorine. Which one? Which one's going to have a higher electronegativity? All right, I'll give you a second. Yep, they're in the same group. They're both halogens. Can I tell you the answer? Okay, so when you go down, the iodine is bigger, which is not attractive, right? So has to be smaller. But don't worry, we'll write it out properly. That was just a prediction, okay? Is this all in there? So electronegativity increases across a period and decreases down a family because they get smaller going across but bigger going down. So the values were actually calculated by a man named Linus Pauling. And so sometimes it's called the Pauling's electronegativity values. That doesn't really matter. The most electronegative element is fluorine. It's also the smallest and the most reactive nonmetal. So sometimes a trick to remember the trends is everything goes kind of towards fluorine, F for fun, except the size. Cesium and francium have the lowest electronegativity. So what you'll see sometimes, the third point there, sometimes electronegativity tables will have dashes or zeros. Our electronegativity table doesn't even include the noble gases at all. So again, when you draw your arrows, then maybe you want to stop at fluorine, okay? These are the last ones. Oops. You can too, yeah. If you don't, that's okay, but they deal with reacting, so it might mess up your brain later. Yeah. Yes, you can, yes. And if you look at when we use this table, it's not even there. Okay, so electronegativity can be a super helpful trend to help you figure out maybe the other ones because there's actually values listed on the back of your periodic table, okay? So everybody should get that one right on the test. Okay, so the next two trends, we can't really draw arrows like that because the two trends are influenced by the type of atom. So the periodic table, this periodic table is simplified. I actually even cropped out the lanthanides and actinides. So what we're going to do is sort of sketch a staircase, okay? So it doesn't need to be perfect. All right, so put in a staircase. Boron, aluminum, silicon, germanium, arsenic, antimony. We'll just do this. You know what? You can just even kind of sketch it. Okay, so everything to the right of the staircase we're going to consider to be a nonmetal. And everything to the left a metal. So we don't even care transition, alkali, alkali earth. We don't care. Size of ions, as long as you remember which ones lose and which one gains, you can think of it like losing and gaining. If an atom gains an electron, then the size is going to increase. So yes, you can sort of think of it like, oh, if I gained weight, I would get bigger. Maybe that's a nasty analogy for you, but it works. So what kind of elements gain electrons? Nonmetals. So if you have something to the right of the staircase, it's going to be bigger as an ion because you have more electrons and the same number of protons. So now there's more repulsion. moving them farther apart. Whenever an atom loses an electron, like a metal, the size decreases because now is less repulsion. And now it's getting closer to the positive. I included this picture here just to emphasize how drastic it is. Again, I am not going to ask you to memorize the picometer size of sodium, but the sodium ion is 97 picometers, which is almost 100 picometers less than the atom. Okay, so it is quite dramatic. Okay, so usually for an ion question, it'll be a metal versus a non-metal. So which one would make a larger ion? Magnesium or chlorine? So magnesium is Mg, Cl. Show me what you think. Which one is larger? I think every question except one was larger. I don't know why I did that, but read the question carefully. Cl or Mg? Yes, interesting. Yes. Yes. That doesn't matter. Amazing. Okay? So, same thing with the next question, reactivity. We have to sort of distinguish whether we're talking about a metal or a non-metal. Okay? So, we're not going to draw summary arrows because that's more difficult to do. So, reactivity is a teensy bit more, requires a teensy bit more brain power, okay? So in the same period, it's the number of electrons that determine reactivity. So you can have a small number of electrons lost or a small number of electrons gained. So it would not be fair to say which one's more reactive, sodium or chlorine, because they lose and gain the same number and they're in the same period. That's like beyond what we need to do, okay? So the smaller the number of electrons transferred, the more vigorous the reaction. Okay, so then this is the two qualifiers that are essentially the same. If an element tends to lose electrons, the fewer it has to lose, the more reactive it is. If an element tends to gain electrons, the fewer it has to gain, the more reactive it is. If you have been enjoying the arrows, then you can I'm not even going to use I'm out of colors. I'm not going to use a ruler this time at all. So it's really towards the outside, like reactivity increases this way and this way. Because how many, and again, we're not even going to include noble gases, how many electrons does fluorine have to gain? 1. So it's more reactive than oxygen, which is more reactive than nitrogen, which is certainly more reactive than carbon. We are made of carbon. Imagine if we walked around and reacted with our environment all day long, every day. We would be very, very sick. And there are, unfortunately, people who have skin issues and all that kind of stuff. So definitely not okay. Metals, the same thing. So this column would lose 1. This column loses 2. I'm going to skip transition. This column loses 3. So sodium is so reactive that you have to store it in oil because it will react with the moisture in the air. Aluminum, you probably have in your home. You cook on it. Are you afraid of it exploding and reacting with the moisture in your food and the air? No. Why the difference? Because aluminum has to lose 3 electrons, making it so much less reactive than sodium, which only has to lose 1. Okay, so our question here, I've done nonmetals together and metals together. So let's do, which is the only fair way to do this. So which one is more reactive? Carbon, which is C, or fluorine, which is F? Okay, I see some Fs. It is fluorine. So this is a case where you do sort of have to remember that when you react, then that's the ions, like losing or gaining electrons, which is only valence. Okay, so let's do the metals. Potassium, which is K, or gallium, which is Ga. Good job. Okay. It is potassium. Okay, so I think there is a periodic table right there. So if you want to draw, sketch it in. But if you don't, it is a little bit trickier to do for reactivity. Okay? Don't draw it on your nice ones that have nice arrows. Don't do that. Okay, so that's a cross. What happens when you go up and down? Again, it depends whether it's a metal or a non-metal. But also, it is sort of logical as well. If you have a larger metal, then it's going to be easier to lose electrons. If you have a smaller, because non-metals gain, when it's smaller, then the nuclei is more attractive. Okay? So again, if you want to sketch some arrows, then we want smaller nonmetals, so that's up. But then it's down because these metals are larger, right? So these arrows aren't so friendly. But I included a periodic table there if you did want to sketch them in, if you're using that as a tool, okay? So again, if I'm going to ask you about a group, then it should be the same type of element. Which one is more reactive? Iodine or fluorine, I or F? Yes, yes. Okay. Again, sort of ignoring the noble gases. And then what about a metal, potassium or francium? So francium is Fr. Yay. Okay, so one of the ways you can summarize is F for fun. Fluorine is the smallest, most reactive, highest electron affinity, highest electronegativity. What else do we do? Smallest ion, all of it. And then francium is the largest metal, smallest ionization energy, smallest electron affinity, smallest electronegativity, and biggest atomic radius. So it's up to you, okay? If you turn the page... Oh, sorry. Yes, francium. Thank you. Sorry. Okay, you do have a few minutes. You can finish your assignment now, or tomorrow's a work period. You can certainly do it then. Please make sure number 5, 4, and 5 are out of 3. So remember what I said. Do not write your answers on here. Make sure you have written enough, okay? And then if you're done that and you're satisfied, you can hand it in. There is a worksheet here in the booklet. When the reactivity patterns in alkali metals and this back one, we're going to do together tomorrow. Okay, so the only worksheet is more practice with trends. Okay, and then there are textbook questions. They're on D2L, they're on the note. You can work on those if you're done your assignment as well. Okay?